My name is Trent Martin. I'm the Vice President of Space Services and the Program Manager for what we call the Lunar Payload and Data Services Program within our company, which is the part of our company that is building, launching, and landing lunar landers on the surface of the moon. I wanted to be an astronaut when I was in fourth grade, and that drove me to aerospace engineering and drove me to NASA, where I worked for many years before joining Intuitive Machines. Intuitive Machines is a company that was founded in 2013 by former NASA leaders, including the former Deputy Center Director at the Johnson Space Center and the former Engineering Director at the Johnson Space Center. He combined forces with a couple of other folks and created a company that was intentionally designed to take aerospace technologies out into other industries. And so for a long time, for 5, 6 years, and still today, we take those aerospace technologies and techniques and we go out into oil and gas and we go into aircraft and other industries. And we intentionally try to infuse different technologies in those other industries. We're definitely a company of space people. We enjoy space. We enjoy the challenge the space industry brings to our work. And when we had the opportunity to bid on NASA's Commercial Lunar Payload Services contract, we jumped at the opportunity because it allowed us to use the knowledge that we had gained over the years and years of experience working for NASA to apply it to a robotic mission to the moon. In fact, multiple robotic missions to the moon. So as one of the primary companies that hold that contract, we have the ability to bid on missions to the moon. And we've won 2 of those missions to the moon, one in 2021 and then a second one in 2022. So we're building what we call our Nova C. The C doesn't mean it's the third in a generation of vehicles ABC. C actually stands for 100. So it's 100 kilograms of payload to the surface of the moon. However, the vehicle weighs almost 2,000 kilograms when we take off. So we launch on board a Falcon 9 rocket. Our Nova C is up in the front end of the rocket. After the rocket releases us on a trajectory towards the moon, we use our own rocket engines to capture in around the moon and then to land on the moon with our own systems, our own LOX methane engine system and our precision landing hazard avoidance system. So that's the spacecraft, the Nova C. In addition to the propulsion systems and the navigation systems, we have computer systems, we have power systems, we have communication systems that talk back to the Earth. So we have all of the pieces that you need to successfully navigate to the moon, land on the moon, and then communicate back to the Earth. The mission in 2022 includes a NASA drill and a NASA science experiment that is looking to drill down into the surface of the moon to look for water ice, and then an instrument to measure what's coming out of the drill cuttings as the drill is drilling down into the surface. In addition, we're flying our own experiment that we call the Hopper, which is a smaller little spacecraft that comes off of the big one and lands down inside of a crater, again looking for water ice. And then on that same mission, we're flying the LTE. But in order to test the LTE, we have to get away from the lander. So we land in a certain spot, and then we want to prove that I can drive away and be checking back, constantly calling back to the lander. And so just like your LTE system works on the surface of the Earth, it works the same way on the moon. We have to drive far away, talk back to the lander, and then we can communicate back to the Earth from the lander. So that's the intent of the rover system, is to give that LTE some mobility, to get further away from the lander than simply talking right on the lander itself. That doesn't really test what you want to test. The reality is that the systems that we typically use in aerospace have a very low amount of data that you can send back and forth between a spacecraft and the Earth or a spacecraft and another spacecraft. LTE offers a different technology that did not exist in that marketplace. And so this test for us allows us to get a much higher bandwidth of data. It allows for future expansion. If you were to build a base on the moon and you wanted to put towers, you could have relay towers of someone, an astronaut say, or a robotic piece of equipment driving away from the base, talking back to a tower, then back to the main base, and then back to Earth. So it gives you a way to create a network, just like a cellular network here on the Earth. It gives you a way to do that on the moon. You can also use the same kinds of technologies in space between satellites, satellite to satellite communication. So it offers a unique new way of doing communications that we haven't really done in the aerospace industry until now. This first test is just that. It's a test. It's to prove that you can use an LTE successfully on the moon. First step is we have to go land on the moon, and then we have to drive a rover out and be checking back. Yes, I can still hear you. Yes, I can transfer data. I can transfer data at a high rate. I can transfer data at a low rate. It works if I go slightly over a hill. It works if there's something in the way. So all of those kinds of tests are what we're looking for on this first mission. It doesn't have a direct impact on the Earth yet, but once you've proven that the technology works, once you've proven that this is a viable system, it opens up new markets, new avenues for using this technology, not only on the moon, but in space, between satellite to satellite communication or spacecraft to ground system communications, which we didn't have before. And it's a much higher bandwidth than what we have been using, simply because it's like using your cell phone. It's just as simple as using this on the surface of the moon, where my Nova C operates as a cell tower and the rover operates as a person driving their car. I always tell my teams, whatever video we bring back from the moon, it better look better than it did in 1969. Otherwise, it's not worth our time. The video systems that we have now require huge amounts of bandwidth if you want to go high definition, which is what you really need to engage the world of today. You have to have high bandwidth data. We're using an S band, but other people use other bands, RF bands, to get back from the moon to the Earth. But even with the largest dishes that we can get on the Earth, a 64-meter dish in Australia, we can get maybe 4 megabits per second of data coming from the moon to the Earth with our radios that we're flying this next year and in 2022 as well. And that's just not a large amount of data. And so anything that we can do to increase that bandwidth is good. Now, I can increase it with LTE from the mobile system like a rover to the lander, but that still doesn't help me getting it from the lander back to the Earth. And so those are some of the areas that we've been looking into, whether it be laser communication or other types of bands that we can use to get from the moon to the Earth, maybe transferring to a satellite that's in orbit around the moon before you transfer back to the Earth. Those types of technologies are what we're looking at. LTE will help us with the ground system on the moon itself, and maybe they help between satellite to satellite communication in the future. But those are the technologies, and increasing that bandwidth to something more akin to what you're used to on your cell phones on the Earth would be ideal, right? You got to match what the movies are doing. And if the movies are talking on the cell phone while they're sitting on the moon back to somebody on the Earth, well, you got to be able to do that. And whether it's science fiction or not, we need to make it reality. So because we only have one shot, we test everything multiple times. We test it in a form factor that we call an engineering unit. We test it in a qualification unit. We test it in a flight unit. And we know that that flight unit was working before it launched, right? And when we land on the surface, we know it's going to be able to operate in the environment that we're planning on driving it in. The temperatures at the South Pole of the moon, minus 200 degrees. It gets very, very cold. And so we need to make sure that you can operate in those types of environments. And it may not just be that it gets that way at night. It may be that if you drive into a shadow or you drove down into a crater, a small crater, all of a sudden you're not seeing the sun and the temperature drops to very, very cold temperatures. You got to make sure that your vehicle and your LTE equipment can withstand those temperatures, or at least know that you're there and get out of it so that you can live for the next test. I think LTE in general could change the entire comm architecture that would be used with spacesuits, mobile systems, whether they be things like the Lunar Terrain Vehicle or even robotic vehicles that want to drive down and look down in craters where you're looking for water ice. The moon, we used to think was just dead, and it's not. There's ice. We know there's water on the moon. So how do we utilize that resource that's available to us? That is the question. And so that's what these early missions are looking at doing. How do you test communication systems? How do you test drills to be able to drill down into the surface? How do you get that ice out of the regolith? And at the same time, it offers a wonderful opportunity for science. So science instruments that can go and operate for a few days to a few months at a location at the South Pole can give you incredible science that you didn't have before and tell you things about the moon that you had no idea about before because you had never gone to look. So we really believe that these types of missions, which by the way are actually fairly inexpensive by relative standards, can give you really, really good return on your science investment. And we're extremely pleased that NASA has taken the opportunity to create a program like CLPS, Commercial Lunar Payload Services, where they can identify a company that can deliver a product. And basically NASA says, we need this delivered to the moon on this day. The amount of data coming back, you figure out how to get there. And essentially that's what we are. We're like FedEx or UPS to the moon. And then we provide them data back as well. And by doing that, it has opened up this entrepreneurial nature of this new space industry that can provide a low cost, reliable service to the moon. And we have 2 of those missions, and we're very proud to say that. And we believe that it will open up a completely different market that didn't exist on the commercial side as well as on the government side. But it needs a little push with NASA's involvement from the beginning. Any type of space flight is a challenge, and you worry about things, but you plan for them. You meet regularly. You talk about the risks that you're taking. You try to take risks that you understand, but there's things you don't understand, right? The United States hasn't landed on the moon, a soft landing on the moon, in a very, very long time. And so there are days where you just have to pinch yourself because you're sitting in a meeting and you're talking about something that you know they talked about in the 1960s when they landed on the moon, but no one has talked about it since then, not in the United States anyway. And then there are days where you're talking about things that have never been done before. And that's what I like about my job, but that's also what makes me nervous about my job is that there's things that we've never done before. And inevitably, when you do things you've never done before, you're going to make some mistakes. As far as the LTE is concerned, what I hope to learn is that, yes, it works as you go over a hill. It works 2 kilometers away. It works 5 kilometers away. It works at a far enough distance that it's meaningful for future missions. So our intent is to put it on that rover. And I hope to put it on our hopper as well, because I'd really like to get some data as we hop down into a crater as to whether or not I can see the LTE across that crater rim, if I can see the signal across that crater rim. And that would be very valuable to me for future missions. When I first came to work at NASA, it was in the mid-90s, and many of the engineers from Apollo were still around. And I had that great opportunity to be able to talk with them. What did they do? How did they do it? It always baffled me that they were able to do what they did, especially with the technology that they had at the time. I will say it is easier for us now with the technology that we have now. It's definitely easier for us. But we're definitely standing on the history, the technologies that they built. And I truly appreciate that. But it allows us to be able to do it at a much lower cost. It allows us to be able to do it much faster than anything that they ever did back then. And that, to me, is incredible. That's exactly what we should be doing as a country in funding programs that lead to eventual markets, that lead to technologies that are meaningful to everyone.